Welcome, everybody. I'm really pleased to be here. I've been to KTH a number of times. It's really one of my favorite places to visit. I love this place. But, I'm going to be talking about some collaborative work, and co-authors are here on the screen, and they've contributed in pretty significant ways to this. And I'd like to just start also that, feel free to interrupt me with questions at any time. I prefer a kind of more interactive style rather than just waiting until the end. So don't hesitate. I'm going to be telling you a little bit of a story about some work that comes from what I would characterize as one of those rare aha moments that you get when you're doing research that happened to me just about 2 years ago, and gave me some insights that took inputs from all of these students. At the time, everyone except Ravi was a PhD student, and kind of an idea coalesced that we then have tried to formalize and characterize. And the primary references for this work are in these archive papers. And the reason that they're in archive papers is that we have tried now 3 times to get the work accepted by major computer science conferences and have been rejected 3 times. And you can make your own judgment about whether that's because of fundamental flaws or the difficulty in conveying the core ideas. I think it's more the latter. And so I beg your indulgence. I'm going to try to explain a concept that I think at least quite a few smart people have found rather hard to internalize. And so it's not going to be trivially easy, which is why I would also encourage you to interrupt me as we go. So let me start, first of all, with some background. So the CAP theorem is a pretty well-known statement that comes originally from Eric Brewer. He first presented this at a keynote conference way back in 2001. And in 2000, sorry, at PODC. And it's really a very trivial statement, and it's a statement about distributed databases. Okay, so when you have distributed databases, it's important that the data be replicated in the nodes across the system. So these databases are typically, they span the globe. So you might have, a data center in Seattle has copies of data records for, airline reservation systems, for example, or something like that. And another one in Singapore also has copies of the data. So the data gets replicated, right? And there's a notion of consistency, which turns out to be a rather subtle notion. But intuitively, it's really pretty straightforward. You would like, when you query the database, for the answer not to depend on whether you're asking in Seattle or in Singapore. You'd like to get the same data for the record, for some record in the database, is this airline seat available or is it not, for example. You would like also for all of the replicas in the database to get updated in a consistent way. So in particular, that sort of notion of eventual consistency turns out to be another subtle notion. But intuitively, it's pretty straightforward, which is it says that if you stop making updates to the database altogether, then eventually all of the nodes will agree on all the values of all the records. So that says very little about the transient situation while updates are occurring. That's where a lot of the subtlety comes in. So that's an intuitive notion of consistency. Availability is the ability of the database to respond to queries. So if you ask the data center in Singapore, is this airline seat available? How long does it take it to give you an answer? Right? If it takes a very long time, the database is not very available. If it responds really quickly, it's highly available. Okay? So that's the notion of availability. And Eric Brewer just pointed out that if your network breaks, network partitioning, the P in CAP is for network partitioning. If your network breaks, you have to give up one of availability or consistency. You cannot preserve both. And that's really obvious, right? Because if your network breaks, Singapore and Seattle can no longer communicate. And so one of them updates a record, the other one's not going to hear about it, right? So you get a query in Seattle for the value of that record, and you now have a choice. You can either not respond because you don't know what the value of the record is, in which case you give up availability, or you can respond with the value that you have cached, in which case you give up consistency, okay? So the theorem is patently obvious once you understand what the terms mean, right? It doesn't really require proof. There were people who, wrote formal proofs of this theorem later after the fact, but they're not really very interesting, right? It's just too obvious to be worth proving. Okay, so from the perspective of software components distributed across a network, you can generalize this beyond databases, right? You just have two views of some value X, and consistency is some notion of agreement on what the value of X should be. Okay, and availability is your ability to respond to queries for the value of X. Okay, and you can see that this problem applies to lots of different scales, lots of different situations. For example, you might be familiar with the cache consistency problem in multi-core systems, for example. Same problem, right? Exactly the same problem on a much smaller scale. There's also a cyber-physical system aspect of this, which is personally what interests me the most, which is where your variable X is somehow representative of the state of the world. It might be the reading of a sensor value, right? And you would like your software components to agree on on some view of the state of the world, okay? Not just abstract numerical values in a computing system. So let me try to give you some intuition before I explain the formalization of this about a key idea, right? Which is that if your network breaks, you have to give up either consistency or availability. But which you give up depends entirely on your application. For some applications, you prefer to give up consistency. For other applications, you prefer to give up availability, okay? And I'd like to illustrate that with two cyber-physical system applications. So the first one is an ADAS system, advanced driver assist system, where you have a camera that's looking forward in the car. The picture here is from a Denso demonstration in 2018. They have a cardboard pedestrian standing in front of the car and a driver trying to drive into the pedestrian, and the ADAS system takes over and prevents the car from hitting the cardboard pedestrian, okay? So you have a system that has this camera, and maybe it's uploading frames from this camera to the cloud to do the image analysis using some neural network implemented there and getting answers back about whether there's a pedestrian in the field of view, okay? But you also have a local system that's got a sensor on the brake pedal, and that sensor on the brake pedal is responding to the driver pushing the brake pedal. And then you have this braking subsystem that is taking inputs from both the ADAS system and the brake pedal, and it's making decisions about applying the brakes, okay? Now, because you know the semantics of the problem, you know what the right thing to do is when the brake pedal gets pushed. Right? You want to respond to that right away, obviously, okay? But software doesn't know the semantics of the problem, right? It has no idea that applying the brake pedal might save a life, right? It just doesn't know that. So you could design this system to erroneously emphasize consistency instead. So if you emphasize consistency, the braking subsystem will not respond to a brake pedal command until it knows what the cloud thinks about what the state of the world is, okay? So put another way, you take a snapshot, your camera takes a snapshot at some time t, okay? Logically, the cloud analysis is giving you information about the state of the world at time t, okay? Same time as the snapshot was taken. And the brake pedal may be slightly later than time t gets applied by the driver, so t plus epsilon. And now, if you emphasize consistency, you should respond to the state of the world at time t before you respond to the state of the world at time t plus epsilon, right? Because otherwise you would be working with an inconsistent view of the state of the world. But that's clearly the wrong thing to do in this circumstance. In this circumstance, you really want to emphasize availability, and you want to respond immediately to the brake pedal push. But let me give you another automotive example that yields the opposite answer, okay? By the way, the images, the pictures, these block diagrams that I'm showing are block diagrams that are automatically generated from a software implementation of these systems, okay, in this language that is called Lingua Franca. So this particular implementation was built by Sarush Baiteni and Ravi Akella from Denso. And so here you've got a scenario where you've got a four-way intersection with a four-way stop, and you have a roadside unit, this RSU at the bottom of the image, that is mediating access to the intersection, okay? And then there's a vehicle simulator called Carla that's being used here to generate the animation that's on the upper right, okay? So you can run this program and see the animation of its behavior, and Sarush has some really nice demos where he shows situations in which the cars crash and situations in which they don't and so forth, okay? But now, the issue here is, when a vehicle is about to enter the intersection, should your software design be emphasizing consistency or availability? And I think the argument here is also very clear once you know the semantics of the problem. You want all of the vehicles to have a consistent view of the state of the intersection before any vehicle enters the intersection. And you want to do that at the expense of availability. If your network breaks and the car cannot make a decision, it shouldn't just plow ahead into the intersection. It should stop, okay? Because otherwise you're going to get an accident. So this is a situation that's sort of similar to the previous one, except that the answer is the opposite, where you want to emphasize consistency over availability. And the CAP theorem tells us that you have to make a choice between those, right? So when you design your software, if you don't think about this, you're going to get a choice by default. And that's not good, right? You need to actually be conscious of what your choices are and which decision you're going to make. Okay, so here you want to emphasize consistency. Okay, so, but what is consistency? Okay, so naively, it's just agreement on the state of some distributed system, right? What do we mean by agreement, right? One of the issues is, okay, can we actually, in a distributed system, agree on the state of something at an instant in time? Well, wait, what's an instant in time, right? In modern physics, we know that there actually is no such thing as an instant in time. And there's no manifold that you can call an instant that separates past and present. If you've studied relativity, it's very clear, okay? But in addition, in practice, in a distributed system, you don't have any shared instant in time. So you can't really ask what the state of the system is at an instant in time in a distributed system because it's distributed and you don't know what the state is at some remote location instantaneously. And so it's practically exceedingly difficult to achieve this naive notion of a consistent view. The problem is even deeper because if you look at modern physics, the very notion of a state of a system is actually on pretty shaky foundations, fundamentally. And you can see this from the perspective of a distributed system. So suppose you've got two physically separated state machines, this one on the left and this one on the right. Okay, they're in two separate places. And the one on the left makes a transition from state A to state B. And the one on the right makes a transition from state C to state D. And now the question is, what's the system behavior? Okay, the system starts in the pair of states AC. And then depending on what order these two transitions occur in, it might go to state BC or AD before it goes to BD, or it could go directly if the two transitions are simultaneous. But actually in physics, there's no such thing as simultaneous transitions. Okay. In fact, in any modern physical model, if these two transitions occur sufficiently close in time, there is no ground truth to which one occurred first. Okay, it's not just that different observers will see different orders, it's that there actually is no ground truth. So this notion of state, the state of the system, is actually pretty foundationally problematic. And so if we base our notion of consistency on this, we're on pretty shaky foundations, because we're requiring both a notion of an instant in time, which doesn't exist and isn't accessible in a distributed system, and we're relying on the notion of the state of the system, which also doesn't exist and has no ground truth. So, so that's kind of a problem. So, but let's look at this from a more practical perspective. How do we deal with this in practice? Because people do deal with this in practice. So let's think about a banking example. So suppose you have a distributed system doing maintaining your bank balance. Okay, so it's using replicated data, and Joe's bank balance starts at $50. Okay, and there's a deposit of $100 at 10 a.m. GMT in London, and a withdrawal in Singapore at 10 a.m. GMT plus 10 milliseconds of $110. Okay, and these are two queries to a database and two queries that change the value of the balance. Now, the question is, should the bank charge Joe for an overdraft? Okay, this is really ultimately a consistency question, right? You would like the two bank balances to agree on in which order these transactions occur, but you have a fundamental problem, right? The fundamental problem is that at the speed of light, Singapore and London are 33 milliseconds apart, which means they're outside of each other's light cone, which means that there is no ground truth to the order in which these transactions occurred. Different observers will see the order being different. Okay, so you can't rely on ground truth to define the order of these transactions. It simply is not, there is no ground truth. Okay. By the way, this image on the left, I asked DALL-E 2 to generate a globe that showed both London and Singapore. This is what it came up with. It invented a name of a new place that seems to be a combination of Singapore and London mashed together in one word. So I was intensely amused by that, so that's why I used it. But that's a complete aside that has nothing to do with what I'm talking about. So how do you do this in practice? Because banks work, and they have solved this problem. How do they solve this problem? Well, they solve it in a pretty straightforward way. When the deposit occurs in London, the computer there consults a local clock and timestamps the event. Okay, it just assigns it a time from the local clock, whatever the local clock reads. Suppose the local clock reads 10 a.m. GMT on the dot. In Singapore, they do the same thing. The computer timestamps the event, and suppose its local clock reads 10 a.m. GMT plus 10 milliseconds. Now here comes the key idea, right? Now we don't take this as any kind of ground truth anymore. We take it as a semantic property of the system. Okay, so now we define that the system, the database system, is required to process these events in timestamp order. Anywhere that these events are processed, they must be handled in timestamp order. Okay, and it's up to you to implement that. You got to find a way to implement that, but it's not easy to implement. Okay, but it can be done, right? You make it the semantics of the database that transactions occur in timestamp order. Now, of course, because you're using local clocks to do this timestamping, you probably want to put some effort into synchronizing those clocks, right? If they're off by hours, you're going to get kind of weird behavior, and customers are going to complain, right? Yes, question.
Isn't there an alternative way to deal with it, which is to say, if we have two events that occur within, within a certain time range that's not too small. I mean, if it's like 1 second, right, maybe we can deal with it. And if they both occur within that, we say, they're concurrent. So we will try to resolve them in a way that's, favorable for the client. So we know that, if we do this one first and then the other, we avoid the overdraft, right?
You could certainly do that, but you're still going to have the problem of how do you determine they've occurred close enough, right? There's always going to be the corner case, right? So you're still going to have to use local clocks.
Right.
And you're still going to have to timestamp those events. And then you could apply that policy, and that would be a pretty reasonable policy, right? I like that. That's a, generous policy towards the user. You could apply the opposite policy too, and because you want to maximize the revenue that you get from your overdraft penalties. So it depends on, your optimization criteria. But you're still going to need to timestamp the events somehow in order to make this determination. And so, but the issue is that now the semantics of the system doesn't depend on how good your clock synchronization is, right? The system can be built to handle these things in timestamp order, no matter how bad the clock synchronization is. And it'll do the right thing from the semantics perspective, but it will be less useful. And customers are going to complain if you don't make some effort to make these clocks somewhat synchronized, okay? So the key idea here is, and this is the one that I think the reason that this paper keeps getting rejected, is that this is a difficult step to convince people of. And the reason that it's hard to convince people of it is that we're not used to thinking about multiple timelines at the same time. In fact, it's really hard to form sentences in natural language that talk about multiple timelines at the same time. At the same time, everything sort of naturally gets referenced with respect to some notion of a global timeline, but we no longer really have that. Okay? And so it's a really kind of difficult concept, but it's this separation of logical time from physical time. And what we mean by physical time here is just what a clock reads. A physical clock is telling us about what time it is. And the fact is that in this distributed system, you have many physical clocks, and they're telling us different things, okay? They're never perfectly telling us the same thing. You can't do that. You can't even define that in physics, okay? So, but what we mean by physical time is what a physical clock tells you. What we mean by logical time is the timestamp that is now treated as a semantic property of the system. Okay, once you've assigned the timestamp, you forget about physical time altogether, and the whole mission of the system is to handle things in timestamp order. Okay, and it can forget about physical time henceforth. So an event is in a model simply occurs instantaneously at some logical time t in some totally ordered set. Every observer sees events in logical time order. This is hard to implement, but we know how to implement. Okay, distributed systems, people know how to do this. But you need to hire an expert, okay? It's not something that you can do naively. Any two events that have the same logical time, this is a number now, logical time, are logically simultaneous. We don't care whether they were physically simultaneous, right? So in the banking system, you'll have to have some policy for dealing with logically simultaneous events because they can occur, right? Even if they have no meaning in the physical world. So you have to have some policy. Okay, so if you think of this, go back to the cyber physical examples, the ADAS system and the braking system, the braking is the ADAS, the ADAS and the intersection, right? You have a software component, updates the value of X, assigns it a logical time. That event gets carried over the network to some remote software component that's going to make some use of that event. And the timestamp is going to be conveyed along with it. But I'm going to show you that it's actually useful to sometimes modify that timestamp as part of the conveyance. Okay. So the receiving timestamp could be different from the sending timestamp. But it's got to be, we impose the constraint that the receiving timestamp is always greater than or equal to the sending timestamp. Okay, so you can introduce a logical delay in a communication, but you can't reverse causality and introduce a logical advance, okay? And I'll explain in a minute why that's useful, because it gives us a way to explicitly give up some consistency. That's the intuition, all right? So we can define the consistency at the sender and the receiver relative to one another, all right? So this is a formula, a definition actually. We define what we call inconsistency because it's easier to define the reverse polarity. So we use C bar for inconsistency. This is the inconsistency from node J to node I is simply defined as the maximum over all the updates on J that are sent to I of the difference between the two timestamps, the sending and the receiving timestamp. Okay, that's a definition. So if you don't modify the timestamp when you convey the message, you're requiring perfect consistency. The two ends have to agree on the value of the variable at a logical time. If you modify the timestamp, you're allowing them to disagree over some region of logical time. Okay, and you get some inconsistency in the view. So we call strong consistency the situation where you have Cij equals 0. The 0 is obscured on the screen here, but you can probably see it on Zoom. So, yeah. So strong consistency simply says that all nodes agree on the value of a variable at a logical time t. The value of the variable now is a function of logical time, not physical time, which gives us a great deal more flexibility and makes the system actually implementable. Whereas when we insisted on it being a function of physical time, it's not actually implementable. So to use this in the car braking system, the camera timestamps the event of taking a frame of camera picture. Now that becomes a logical time. The braking assistant computation, which may occur in the cloud, is logically instantaneous because it's going to tell us about the state of the world at the same time as when the frame was taken. So the logical time is still T1, regardless of physical time, no matter how long it takes to upload this to the cloud, get the result back. The timestamp is still T1. When the brake pedal gets pushed, that gets assigned a logical time by consulting a local clock. And now if we require strong consistency, we require that this brake component wait for the response from the cloud before it can process the response from the brake pedal, because we're requiring it to process events in timestamp order, right? And that's clearly the wrong thing to do. It's going to cost us in availability, which is not what you want in this particular application. Availability, we can quantify that too. That's easy to quantify, actually. We quantify the converse, unavailability. So the unavailability at node I is the maximum over all accesses of a shared variable at I of the difference between the physical time on a local clock of the access to that shared variable and the logical time at which that shared variable, the logical time that that shared variable has, okay? The timestamp of that shared variable. So in other words, if you try to access a shared variable that has some timestamp t, and the system has to wait a while before it can be sure to give you the right answer, right? That's the unavailability. So this is a relationship between logical time and physical time. We have a similar constraint, which is that this unavailability is always greater than or equal to 0. And perfect availability is where the system is designed in such a way that it can always respond immediately. Okay. We have, yes, question.
Why is there a non-negative constraint? This could be the physical time be quite out of sync.
Yes, but the there's a bit of a technicality here, and actually it doesn't have to be non-negative, okay? But in practice, you often want to delay updates of a variable until your local clock matches the logical time of the update. And the reason for that is to be able to accept asynchronous events from outside that are going to get timestamped with your local clock. Because you want to be sure that you've seen all of those before you do the update in order to ensure that you do the updates in timestamp order. Okay, so it's a bit of a subtle reason, but there are circumstances, for example, if you happen to know that there are no asynchronous updates coming in locally, so you're not going to use your local physical clock to timestamp anything, then you can go ahead and update the variable before the physical clock matches the logical clock, the logical time. Okay, but it's a bit of a technicality there. But the general constraint is that you constrain this to be greater than or equal to 0, and you're guaranteed to be okay then. Okay, there's one more offset. Well, actually, there's two more offsets that we have to consider. One is that I mentioned that you have to hire an expert to make sure that the software ensures that every component sees events in timestamp order. Okay, I'm not going to explain to you the mechanisms for doing that, but you can see that the software, every once in a while, when it sees an event with a certain timestamp, is going to have to wait before it can safely process that event with a timestamp because it's not sure whether it's seen other events that have earlier timestamps. Okay, so in practice, that software often has some waiting time. That waiting time we call a processing offset, and that's defined also as a time difference between physical time and logical time, except that it's very similar to unavailability, except that the unavailability is a delay in reading a variable, whereas this processing offset is a delay in writing a variable, okay? And you're delaying it in order to ensure that updates to the variable are handled in timestamp order. Okay, so we call that the processing offset. By the way, it's this processing offset that yields the constraint that the unavailability is greater than or equal to 0. Okay. All right. There's the last quantity that I'm going to define is the latency, right? The CAP theorem had three quantities: consistency, availability, and network partitioning. Well, network partitioning is just an extreme case of a slow network. But all networks have delay. And it turns out that consistency and availability have to be traded off in all networks, regardless of what the delay is. Okay, so we can quantify the latency, and we define apparent latency. So the apparent latency for a communication from node J to node I is the maximum over all messages from J to I of, again, a difference between a physical time and a logical time. The logical time of the original update now at node J and the physical time at which the message is received at node I. So notice that this is comparing a physical time using a local clock to a logical time received from a remote site. Okay? It's really important that it is not comparing two clocks, which is really hard to do in a distributed system. It's only using the local clock and the timestamp that came in on the incoming message. We call it apparent latency because it looks like the latency to you, but is it really the latency? We don't know, because the clocks could be out of sync. Okay? So this quantity, however, is trivially easy to measure. You just look at your local clock, you compare it against the timestamp, you know what it is. You know what the apparent latency is, right? You can think of the apparent latency as consisting of the sum of four quantities. The processing offset affects it, but so does execution time. This Xij is execution time along the path of the message. So does network latency. Lij is the amount of time it takes the message to traverse the network. Eij is the clock synchronization error. Okay. I'd like to point out that these three quantities, the X, the L, and the I, are all extremely hard to measure. But the L is trivially easy to measure. You can measure the combination of these numbers, you just can't measure them individually. All right. So you can put these four quantities together into this rather beautiful theorem. The unavailability in a system is the maximization over all of the communications to I of the processing offset and the maximum over all J's sending to me of the apparent latency minus your tolerance for inconsistency. Okay, and this theorem actually follows immediately from the definitions. So a proof of this theorem looks just like repeating the definitions. There's another, well, so in words, what this theorem tells you is that the unavailability is simply the larger of two quantities. It's either determined, it may be dominated by the local processing offset needed to ensure that things are processed in timestamp order. So in other words, it's your software delays that you've inserted, or it's dominated by the apparent latency minus the tolerance for inconsistency. And this is where the CAP theorem becomes obvious, right? The fact that the tolerance for inconsistency is subtracted out means you can compensate for network latency by tolerating more inconsistency. Right? So increasing tolerance for inconsistency improves unavailability. There's a beautiful matrix formulation of this in a max plus algebra. So it's an alternative algebra where addition is replaced with maximization and multiplication is replaced with addition. And you take all of these apparent latencies and put them in a matrix that represents the pointwise apparent latencies. So you can have a completely heterogeneous network. You can have a network where, you know, some of the communications are going locally over a very fast bus. Some of them are going over, wireless network. Some of them are going over Ethernet. It doesn't matter, right? You can have a very heterogeneous network, and the matrix represents the structure of the network and the apparent latencies in the network. And you get this nice linear equation in a max plus algebra that relates the unavailabilities to the apparent inconsistencies and the apparent latencies, tolerance for inconsistency, and processing offsets. So how do we use this theorem? Well, we sort of stumbled on this theorem from the applications rather than from the theory, okay? Because we were building this programming framework. It's a coordination language called Lingua Franca. And we were observing that, hey, you know, we can trade off consistency and availability here. And if we don't do it intelligently, we get weird, unacceptable delays in our system. And in fact, the first observation of this came from Christian Menard, who's a PhD student in Dresden, at the Technical University of Dresden. And he was implementing an AutoSAR test case for the ADAS system, the braking assistant, okay? And he implemented that in Lingua Franca and said, you know, this is weird because it's doing the wrong thing. You know, when I apply the brake pedal, there's going to be a delay that's going to be determined by the time it's taking to analyze this image. And I said to him, that's because you're insisting on strong consistency. And I suddenly realized, wait a minute, this is related to the CAP theorem. And I had never made that connection before. And so that's what led to being able to quantify these things. So the way a Lingua Franca program works, it's a coordination language. So you create software components in a target language. And the target languages that it currently supports are C, C++, Python, TypeScript, and Rust. So those five have good support. There's a couple of experiments to add other languages, but not very mature yet. And it's got this interactive visualization that was developed by Reinhard von Hangsladen's group at the Technical University at Kiel in northern Germany. So these diagrams that I've been showing all along, all the diagrams except the ones created by DALI 2 were created by this diagramming tool from Reinhard's group. And they're created automatically from the source code. Okay, so they'll show you all the architecture of your software as you're building it. So let's look at the braking example. So in the braking example, you've got your software components, this is the diagram for a Lingua Franca program, right? So the camera component is grabbing a snapshot from a camera. The braking assistant is doing the vision analysis on it. This component is sending it over the network and introducing an inconsistency. Okay, what it does is it adds 10 milliseconds of logical time to that event using this syntax. This is how in the program, this is how you make the connection. You say vision.out connects to braking.in after 10 milliseconds. And that says the timestamp at the receiving end will be 10 milliseconds higher than the timestamp at the sending end. It's an explicit tolerance for inconsistency. And what does that buy you? Well, that means, let's look at it, right? So if this braking assistant and the network latency together are less than 10 milliseconds, then the apparent latency will be such that you can go ahead and process the brake pedal input immediately, as soon as you get it. Push the brake pedal, it gets timestamped using your local clock, you process it right away. Okay, so by expressing this tolerance for inconsistency, you are very explicitly saying, I am allowing the braking system to handle data that's inconsistent up to 10 milliseconds in order to compensate for physical delays that are occurring in the network and the computation. Yes.
So conversely, if you don't have this after annotation, you enforce consistency.
Exactly. And so that was my answer to Christian. When he showed me this example, I said, just put an after delay in there and your problem goes away. And yes, back there.
So once it's received the command from the braking assistant, how does it know not to process that immediately and wait potentially for something else to come in, which has an earlier timestamp?
Well, we do make an assumption that the network communication does in order communication. So if you have just one network path from this vision to the braking system, right? We assume that that's implemented using something like TCP/IP, and so it's in order reliable delivery. And so you won't get, if you get a message with a timestamp here, you know you're not going to get a later message with an earlier timestamp.
Yeah. The physical brake would arrive later, but might potentially have an earlier timestamp. So
yes, well, right, but this relates to your previous question about the unavailability, right? So when I get an incoming message with a certain timestamp, the braking system will wait until my local physical clock matches that timestamp before it processes it, in order to ensure that it doesn't preempt a command from the brake pedal, right? Which will will use the local clock to timestamp its event, right? So you're asking the same question in many different ways, which is great. So if you put this example into the Cal Theorem very specifically, you can actually go a step further. You can also specify requirements on your unavailability. So we do that using deadlines. So in particular, so this in Lingua Franca, the program that actually responds to an asynchronous external event gets rendered something like this. And this little diamond with a P in it is a hint to you that there is an event that can appear here that is going to draw its timestamp from the physical clock. The P is for physical here. Okay. So when the brake pedal gets pushed, an event appears with a timestamp drawn from the physical clock. It triggers a reaction, which then drives this braking assistant, which has a deadline then, and a very tight deadline of 3 milliseconds in this case. That's your tolerance for unavailability. You're stating that I'm okay with handling this event up to 3 milliseconds later than its timestamp, but no more, right? And then my tolerance for inconsistency is specified with this after delay on the connection. And you can just plug those into this max plus formulation and derive your bounds on computation times and network latency from that. And in fact, what you find out is that you actually have 13 milliseconds, which wouldn't be surprising, right? You can probably guess that this deadline will not be violated as long as the pedestrian detector plus the network latency plus the clock synchronization error is less than 13 milliseconds. Okay, and the Cal theorem just spits that out for you, and you're done. Okay, so that gives you the requirements on the network. Here's the calculation using the Cal theorem. This is execution time at the local end, right, which you can also just take into account in the 13 milliseconds. So anyway. So you have this requirement now that your computation time and your network latency should not exceed 13 milliseconds. And as long as it doesn't, your system will behave as specified. The deadline won't be violated and consistency will be maintained. What if your network breaks, right? And the 13 milliseconds goes out the window. What happens? Well, the Cal theorem and its specialization of the CAP theorem tells you have a choice. You can now either sacrifice availability or you can sacrifice consistency, right? Beyond what the program has specified as the requirements. You have to do one or the other. So which should you do? Well, it turns out that the infrastructure that Soroush had built for distributed execution in Lingua Franca gives us this choice. He built two different coordination mechanisms, one that we call centralized, one that we call decentralized. And the centralized coordinator, when the network breaks, will always sacrifice availability. So it's the right thing to use for the intersection example. The decentralized one will sacrifice consistency when the network breaks and preserve availability. So it's the right one to use for the ADAS example. Okay. And we didn't realize this. We thought that the difference between these was more about efficiency and not something fundamental, but it turns out it's really fundamental. It tells you how the system is going to react when your assumptions about your network behavior are violated. Okay. You can go further in Lingua Franca and throw consistency out the window altogether and use what we call a physical connection, which is the syntax is like this. You use a little squiggly arrow, okay, which gets rendered in the diagram as a squiggly line. And what this means is essentially that the timestamp at the sending end is discarded, and a new timestamp is assigned at the receiving end from the local physical clock. And if you think about it, this is probably what someone would have done intuitively with this system design if they didn't know anything about the Cal theorem and about distributed computing. They're just going to process the brake pedal system as soon as they see it, and they're going to treat the incoming messages non-deterministically whenever they arrive, right? But there's a real big downside to doing it this way, which is that your system now becomes non-deterministic, even when everything is behaving correctly, which makes it much harder to test. Okay, and in a more complex system, you could get messages now that are going to arrive out of order in unexpected ways. So the student Soroush, who built the distributed execution, he took a self-driving car stack called AutoWare.auto. That's an open source self-driving car, ported it to Lingua Franca, but he showed that the original implementation, it actually has non-deterministic communications, and it happens very rarely, but it can get into these inconsistent states where the controller thinks the car is in forward gear and moving in reverse, or it's in reverse gear and is moving forward. And if a car was actually in that state, that's probably a really serious condition, right? It probably means that you've had a crash. But this inconsistency is happening only because messages are arriving in non-deterministic order, because they're using this style of messaging instead of the time-stamped messages. So I've just about used up all my time, but I just want to kind of give you a quick assertion that we can go back to the banking example and implement that in Lingua Franca. And that's a little more interesting than the examples that I've shown you because it's a feedback system. Okay, whereas the examples that I showed so far are just feed-forward systems. Actually, the four-way intersection example is a feedback system also, but the ADAS system, everything is flowing in one direction. All the information is flowing in one direction. So, but the banking example has feedback in it. And so that makes it a lot more interesting to implement. The Lingua Franca program that specifies the structure of the application looks like this. The rendered diagram looks like this. This says, okay, you've got n instances of user input, n instances of replicas of the database. These are the connections. And user inputs are responding to physical actions. So they're coming in asynchronously into the system. We're using the local clock to timestamp them. And those updates are getting broadcast to the system. And this system has no after delays. So it's designed to deliver perfect consistency. And you can use the Cal theorem now to derive the unavailability that results from that as a function of your network latencies. And you can implement this using either our centralized coordination, in which case you maintain consistency if the network misbehaves at the expense of availability, or you can use it using the decentralized coordination, in which case you do the reverse. You preserve availability at the expense of inconsistency. So I'll skip over the details there, but there's a lot of depth there. So just to summarize what I've talked about, okay? The CAP theorem, obvious theorem, right? The Cal theorem, not so obvious because it requires this rather subtle notion of how to define consistency and how to quantify it, right? Centralized coordination preserves consistency for all network latencies. Even if your network breaks completely, it'll preserve consistency, but at the expense of availability. Decentralized coordination preserves availability for all network latencies. You always get a response from the system within bounded time, but at the cost of consistency. In both cases, you can put in fault handlers. The deadline construct in Lingua Franca allows you to specify a fault handler. If the deadline gets violated, do this. Okay? Similarly, with decentralized coordination, you can put in fault handlers that say, if I get a message with a timestamp that is out of order, consistency has been lost, I can specify a fault handler that handles that situation. Okay. So a much shorter summary. I see this result as almost like a Heisenberg uncertainty principle about distributed computing. It says certainty takes time. Certainty in this case is consistency, and time is availability. And it's a fundamental trade-off. It's absolutely, there's no way around it. Got to give up one or the other when you have delays, network delays. And if you have a programming framework that enables you to give them up in intelligent ways, where you actually can reason about how your program is giving up consistency or giving up availability, that's so much better than just building a program and getting what you get and discovering it when you deploy it, how it's going to behave when the network malfunctions, right? That's the alternative. So anyway, so with that, these are the references, and thank you very much.